Ah, Welcome back, everyone. So for the last talk of the day, we're pleased to have Anna Schilling at UC Davis, who will tell us about an uncrowding algorithm for hook value tableau. Very topical, given the past year.
Yeah, thank you very much to the organizers for giving me a chance to talk. And yeah, as you just mentioned, uncrowding fits very well with the pandemic. Francois is already putting his mask on. So this is joint work with my students, Jinping Pan, Joseph Pape, and Wenchen Po. Jinping will actually move next week or the week after to North Carolina State University, but the other two students will be on the job market in the future, so watch out for them. So the good thing is that Marino already talked a lot about symmetric functions. So my talk will also involve a lot of symmetric functions. So my plan is to first give you some background, motivation, and definitions. Then I will talk about this particular uncrowding on the hook value tableau, and I will give you some applications at the end. So let me first sort of start introducing the main player. So let's first begin with what's called the stable symmetric Grothendieck polynomial. And as Marino explained, if you look at the Schur functions, so S lambda, you have a shape lambda, and then you fill that shape lambda with numbers such that they're weakly increasing in rows and strictly increasing in columns. So those are semi-standard tableaux. And if you sum over all of those, you get the Schur function. So for the stable symmetric Grothendieck polynomial, there's a similar sort of combinatorial formula where you sum over set value tableau or semi-standard set value tableau, also of a given shape lambda. And so the difference is basically that instead of filling every box with a number, you are now going to fill those boxes with sets, non-empty sets, okay? And I need to explain to you what I mean by semi-standard, so what this weak increase in rows and strict increase in columns is. But you can already see that it's very similar to the Schur function. So you sum over some sort of tableau, and then you take x to the weight. So x to the x1 to the number of ones, x2 to the number of twos. And well, there's also this extra parameter beta, which sort of measures what's called the excess. So if you think about it, if you think of the Schur function where every box has just one element in it, if you fill them with sets, you can count how many sort of extra numbers there are beyond the sets. And that's called the excess, and beta sort of keeps track of the excess. Okay, and well, how do we define semi-standardness? Our entries A, B, C are now sets. So we compare them by taking the minimum and maximum of all the sets. So we want that the maximum value of the sets in A should be less or equal to the minimum number in the values of the set B. So that gives us a weak increase in rows. And we want that in the columns, the maximum of A is strictly less than the minimum of C. So that's our semi-standardness condition. So here's a quick example. Down here, I have a couple of supposedly set value tableau. And if we look at the first one, you can see that well, if you take the maximum of 1, 2, it's 2. And if you compare it with the minimum of 2, 5, that's also 2. So you have weak increase. And if you compare columns, also everything works. But for example, for the second tableau, we have a 3, 4 and a 3, 5. So the 4 is strictly bigger than that 3. So that is not a semi-standard set value tableau. And similarly here in the last one, the column doesn't work, right? The 4 is bigger than the 3 above, so that is not semi-standard. So in this case, the only one that works is the first one. And for the excess, so the first one has excess 4 because I have sort of 4 extra letters compared to a semi-standard Young tableau. So the excess would be 4. So I hope it's clear what the objects are. And so these stable as I just said, the stable Grothendieck polynomials generalize the Schur functions, and they actually come from the K-theory of the Grassmannian. And I won't go too much into the details of the relations to geometry, but one observation is that the Grassmannian has some sort of duality. So if you look at K spaces and N space, then there's a duality with respect to N minus K. And in terms of symmetric functions, Marino has introduced the omega operator also, which takes the Schur function to the Schur function indexed by the transpose partition. So the question is, does the stable Grothendieck polynomial also have some sort of nice interpretation under omega? But it's not true that if you take omega of the stable Grothendieck, it's the stable Grothendieck with lambda transpose, okay? So the question is there some other duality that would do this? Or is there some other sort of symmetric function that behaves nicely with respect to the omega? And the answer to the last question is yes. And these will be the canonical stable Grothendieck polynomials. So, and they will play a major role in this talk. So instead of just having one parameter, for us, the beta, this is actually indexed by two parameters, alpha and beta. And if you act with omega on this one, it interchanges the two parameters, beta and alpha, and it transposes the lambda. And I will introduce, I will give you a combinatorial and way of writing these canonical stable Grothendieck's in a second. And so we saw the semi-standard set value tableau. So the combinatorics associated to the canonical stable Grothendieck's will be what are hook value tableau. And before I tell you what these hook value tableau are, let me just briefly give you like a summary of all the various polynomials. So we saw the stable Grothendieck's. The combinatorics are set value tableau. They're also stable weak symmetric Grothendieck's. And so instead of sets, you actually enter multi-sets into the boxes. They were introduced by Lam-Piliavsky. Then there are duals to these, and the combinatorics involves reverse plane partitions. And then the ones that will be important in this talk are the canonical Grothendieck's, and they will involve the hook value tableau. Okay, so now let me actually explain what these hook value tableau are. And the basic idea is we want to combine sets and multi-sets, right? And if you look at a hook, and this is now just a usual sort of semi-standard hook, then if you look at the row is weakly increasing. You can think of the row as a multi-set, and you can think of the column as a set because their elements cannot repeat, right? So a hook sort of combines multi-sets and sets. So that's why these hooks actually come up. Just some terminology. So this element here in the corner, the X is called the hook entry, then the A's are called the arm, and then the legs, the things in the column are called the leg. And I also sometimes use the extended leg, which includes the hook entry. And I need to tell you, well, how do we get a semi-standard hook value tableau? So again, we look at the shape lambda, and now we are going to fill these entries with hooks, right? Rather than sets or multi-sets or just numbers. And we compare them exactly as before. We look at the maximum of all the elements in the hook, and we compare the maximum versus the minimum. And it's weakly increasing in the row and strictly increasing in the column. Okay, so that will be our semi-standard hook value tableau. So here's an example. Here the red numbers are sort of the arms, and the green numbers are in the leg. And you can check that, and unless I made a mistake, that if you look at the minimum of one entry and the maximum of an entry to the right, then that should be weakly increasing in a row and strictly increasing in the column. Okay, and well, the canonical stable Grothendieck polynomials are now generating functions over these hook value tableaux, right? And we do the same thing. We take x to the weight, but since we now have arms and legs, we have two parameters, alpha and beta, and the alpha just sort of measures the excess in an arm, and the beta measures the excess in a leg. Okay, so those are the two parameters. Okay, so my other two students, Graham Hawkes and Travis Grimshaw, they actually defined what's called a crystal structure on these hook value tableau. So what does a crystal do? It sort of puts a graph structure on these elements, on the set of all hook value tableau, and there will be colored edges between these vertices. So the vertices will be all those hook value tableau. And if you can get a crystal structure, you sort of automatically get a Schur expansion of the underlying symmetric functions. And that's because the crystal basically gives you some sort of mimics a GLN representation, and the S lambda are the characters of the crystals. So that's why it's nice to have the crystal structure on certain sets, because on symmetric functions, it gives you the Schur expansion. So let me just briefly go over how this works. So what you do is you take your hook value tableau and you read it column by column, left to right. And within the column, you read the extended legs first, and you read them from top to bottom, and then the arms you read from bottom to top after that. Okay, so that gives you a reading word. So here's an example. So the first column in this example reads, well, I first look at this column, so that gives me a 4, 3, 2, 1. And then the arms I read after that from bottom to top, so that gives me the 4, 1. Okay, and then for the next column, you do the same thing. You first read the first column, which gives you the 5, 4, 3, 2, and then you read the arms in increasing order, so the 2, 2. And then you just concatenate these. And then to get the crystal, you need to do some pairing. So for the crystals, you have an operator fi for every I in your alphabet, basically. So if I want to explain what the fi operator does, I need to tell you how the i's and I+1s pair. And in this reading word, whenever you see an I+1 before an I, you bracket them, and you do that successively. And then at some point you will be left with just i's followed by I+1s, and then the fi sort of picks the rightmost I, and you want to sort of act on that letter. So here are a couple of examples. Here's our reading word for this example. If I want to do an F1, I look at the 2s and 1s. And so this 2, the first 2 and the 1 are bracketed, right? And then the next 1 and the next 2 are unbracketed. So the thing that is circled is sort of the rightmost one. And then I have more examples that you can go through, but they sort of follow the same pattern. Okay, so that's determining which letter sort of you want to focus on. But then the crystal operator sort of takes a cell where that circled letter is, and then depending on various situations, various things happen. So let's first look at this case N. So in that case, the fi operator just changes that I to an I+1. And here is an example of that case. So here I have my T. This one here was, this one in the leftmost corner was the one that was circled, and that just changes into a 2. Okay, but then there are other sort of situations, namely if an I+1 is above, in the cell above or to the right, other things happen. So if there's an element to the right, so this I think is no, sorry, this is a case above. So here I would like to take the 3, but there's an I+1 above. So then the I+1 sort of moves a cell up. And similarly, if you have something to the right, also something happens. So I mean, this describes how things move around in these cells, so that at the end of the day, you again have a hook value tableau. Okay, so these are well-prescribed combinatorial operators. And as I said, so one thing that you get from these crystal operators is a Schur expansion. But now let me get to this, to these crowding maps. So what do they have to do with this? So what do the crowding maps do? So you have these cells filled with a lot of things. So they're sort of crowded, right? You have them filled either with sets, multi-sets, or these hooks. And the uncrowding sort of wants to uncrowd the cells so that at the end of the day, there's only one number in each cell, which is the uncrowding. So you basically have, you know, you have separated everybody. Everybody's 6 feet apart in each of their little cells. And this was done for set value tableau. So the crystal structure in this case was given by Monica, Pechennik, and Scrimshaw. And there is, in fact, an uncrowding map, which was given by Buch. For the multi-set case, there's also a crystal given by Hawkes and Scrimshaw, and they have also given an uncrowding algorithm. But for these hook-valued tableau, up to now, no uncrowding map was known. So what this talk is about is to actually give you this uncrowding map. Okay, and the nice thing is that these uncrowding maps intertwine with the crystal operators. So we actually have crystals on semi-standard Young tableau, and if you do this uncrowding at the end of the day, you end up with a semi-standard Young tableau, and the crystal operators on these various tableaux, set-valued, multi-set, hook-valued, intertwine under this uncrowding map. Okay, so that's why it's nice, and having this uncrowding map also gives you symmetric function expansions, which I will talk about at the end if I have time. Okay, so for the set valued case, this uncrowding operator was given, has appeared in a lot of papers. And let me just explain this in terms of an example. That's the easiest. So here is a set value tableau. So I've now written things in columns because that sort of relates to my hooks, right? The sets are sort of in the columns of my hook. And what you do is you look at in French notation, the highest row that has multiple elements in a cell. And then you look at the largest one that appears. So here, my second row has a 5, 4, right? And that is the largest one. And then what you do is you take that largest letter and then you just RSK insert it into the next row, right? So you take the 5 and you RSK it into the next row. Then you repeat. So then my next letter here is the 4. The 4 wants to uncrowd, and you RSK it into the next row, and it bumps up the 5. And then you repeat, you take this 5 here, and you uncrowd, so you get this. And then the last one would be the 2 in the bottom. And again, you RSK it, you insert it, and it bumps the 3, which bumps the 4, which bumps the 5. So at the end of the day, once you do this uncrowding, a set value tableau becomes a semi-standard tableau. And by the way, there's also a recording tableau, which will come in later, which is a flagged increasing tableau. And if you keep track of the recording tableau, this is in fact a bijection. Okay, so now let me go to the uncrowding for the hook value tableau. And since I've just described for you the uncrowding for the set value tableau, our uncrowding will just uncrowd the arms. Once you've uncrowded the arms, you can uncrowd the legs using what I've just described, right? So I will focus on how you uncrowd the arms. The algorithm is sort of similar to what I've just described, except that instead of going up, you actually go to the right. So you go to the rightmost column that has multiple things in an arm, and then again, you take, you find the topmost element that has something in the arm, and then you sort of do some uncrowding in this arm. Okay, and again, I'm going to do that in terms of an example. So here, this element here, this cell here with the red 3 is the one that has multiple things in an arm, and it's sort of like the rightmost and topmost. And then that 3 wants to uncrowd, and then you look in the next column for a letter that's greater or equal to it, which is the the green 3, and it will sort of bump that out. So the column here is, yeah, the red one is in column 2, row 2, and the thing that it will bump is of value 3, and in this case, it just bumps it out. Okay, and then you repeat, like now we have an arm in that column, and you sort of repeat. But there are several scenarios which I will briefly go over that can happen. So if you have this element A that you want to uncrowd, either you uncrowd it into something in the same row or in a row below, and you have to sort of distinguish these two cases. So if it's in a row below, then either you just create a new cell, or if there was such a K which was bigger or equal to this A, then, which is the second case, then you take that K and you bump it out. So that's in the case when the two are not in the same row. If it's in the same row, something sort of more complicated happens. This element that you bump out sort of takes something in the leg with it. Okay, so if you, again, if it creates its own cell, then it takes everything that's greater or equal to it with it into the leg. And if there is something that it can bump out, again, it will take this tail with it and bump out the K. Okay, so these are just the various cases. And well, to define this uncrowding operator, so we will go from a hook value tableau to a set value tableau, since we are only uncrowding the arms, and then a recording tableau, which is a column flagged increasing tableau. And this column flagged increasing tableau basically just keeps track of how far a particular letter moved to the right. So that's what it does. Okay, and here's an example. Here's my T. If you uncrowd this 6, this red 6, if you sort of go through these cases, then the first row gives you what the uncrowding does. You can see that 6 sort of moved 2 boxes to the right. So that's why in this recording tableau, I have something here labeled with a 2. Then you still have this 1 here, which we need to uncrowd. If you go through this algorithm, that 1 ends up moving 3 things to the right. And that's why in this recording tableau, I have a 3 in that box. Okay. So now let me briefly give you a couple of properties that this uncrowding has. So
can I interrupt you for a second? I just have a quick question.
Yes.
Yeah, is it obvious that when you do this uncrowding algorithm, you're always going to get, like, if you have 2 different set value tableau, that the uncrowding algorithm will give you something different? Or is it possible that you get the same standard tableau at the end, or semi-standard tableau at the end?
You could get the same semi-standard one, but then you would have a different recording tableau.
Okay, so the recording tableau can actually distinguish between the two, but you don't necessarily get different images. Cool. Thank you.
Yeah, so no, the proof is actually like several pages long. It's very nitty-gritty, so it's not obvious to
Just
see.
making sure. Cool.
But you do need the recording tableau to keep track of things. Yeah. Okay, but the nice thing is that this uncrowding actually commutes with the crystal operators. Okay, so we had crystal operators on set value tableau, we have crystal operators on these hook value tableau. And if you do that, so if you do the uncrowding, this F commutes with the P, with this uncrowding. But it leaves the recording tableau invariant. Okay. And similarly for the E, so basically we have a commutative diagram. And another corollary that we get from this is that we can immediately say that this crystal on the hook value tableau is indeed a Stembridge crystal, because the one on the set value tableau is a Stembridge crystal. Or if you keep uncrowding and also uncrowd the legs, then that's even more obvious, because on semi-standard tableau, we know it's a Stembridge crystal. And another corollary we immediately get is that it's Schur positive, because the highest weight elements actually give you the Schur, the highest weight elements in the crystal actually give you the Schur expansion. Okay, and one last corollary I would like to mention is, so I mentioned that there was already an uncrowding operator for set value tableau and for multi-set value tableau. So for the multi-set value tableau, that basically means you don't have any leg, right? And our operator coincides with this one when we don't have any legs. Okay, now, since I said that this actually gives you a bijection, if you keep track of the recording tableau, I need to give just one word of caution that unlike in the set value tableau case, where the recording tableau can be all possible flagged increasing tableau. So flagged increasing basically just means it's semi-standard, but in row I, the value has to be less or equal to I. And so for us, it's in the column way. So in column I, the value has to be less or equal to I. We don't actually get everything. We don't get all column flagged tableau. So for example, here, if you try to sort of crowd back this example, then you can't make it happen. And we call this, like, this particular cell practices social distancing. And so we had to sort of go through some recursive procedure to actually say what is in the image under this map. So we had to characterize the image. And I don't want to go through this since I have only limited time, but it's not the whole set, it's just some subset K. And we have sort of specified what this set is. Okay, so in the last couple of minutes, let me just briefly go through some applications. Namely, we can, instead of just getting Schur expansions, we actually can get some other expansions. And this actually uses some results of Bandlow and Morse, which gave what are called tableau Schur expansions. So a symmetric function is said to have a tableau Schur expansion. Well, if you can write this F in terms of as a sum over some set of tableaux, and then you take the weight of these tableaux, and then you have the Schur function indexed by the shape of the tableau. If you have something like this, then you automatically get the expansion in terms of the Grothendieck and the dual Grothendieck polynomial. So that's a theorem by Bandlow and Morse from 2012. Okay, and now we are just going to apply that to our setting. So we do have that these canonical Grothendieck polynomials have such a tableau expansion. So we can write them in terms of certain tableau. And then you take the weight of the tableau S to the shape. So that basically comes from our crystal and the uncrowding. And there's an explicit way of describing the set T and the weight. So that's all explicitly given using this uncrowding. And by this Bandlow-Morse result, we can therefore also give the dual Grothendieck expansion and the Grothendieck expansion of these canonical Grothendieck polynomials. So here is our Schur expansion of the canonical Grothendieck's, right, which we get from the uncrowding or the crystal. And these tableaux that you get are basically all the semi-standard tableaux that can be crowded back to a highest weight. Okay, so sorry, the set S is all the tableaux that can be crowded back to these tableaux that appear in the set T. So for example, if you just look at the shape 2, there's only one tableau that crowds back. But if you look at the shape 2-1, there are actually 2 tableaux that can crowd back to the shape, or uncrowd to the shape 1-1-2. Okay, so that's our set S, and then the G can be written in terms of the dual Grothendieck's by sort of summing over the set S by this result by Bandlow and Morse. So we get an explicit formula of the G's in terms of the little g's. And similarly, I haven't actually written it out, but similarly, you can also do that in terms of the Grothendieck polynomials. Okay, so that's basically all I wanted to say. And if this was a little bit technical, here's one thing you should take away from the talk, which is the reading word. So if this is our hook valued tableau, right, then how you get the crystal? Well, you first read the first column, thank, and then you read the first column from bottom to top, U4, right? And then you take the second column and you read it down, your time. So thank you for your time, and I hope you at least got this out of the talk.
Thank you.
Awesome. Thank you. Thank you, Anne. Do we have any questions?
So I have a question, but there was also a question before mine in the chat by Francois. I don't know if it got answered about whether there was an RSK flavor of explaining the crystal operators.
Yes, I mean, first for Francois' question, yes. So one way to explain but just for usual semi-standard tableau, the way that you can explain the crystal operators is actually by doing, let's say, a row reading or column reading or any sort of reading that if you take that word and you RSK it back, you get the tableau. Yeah, so you take a reading word of your tableau and you can just describe the crystal operators on words. So you have a word and you do this bracketing in terms of the words. And the result is that under the crystal operators, the recording tableau actually never change. So you can always RSK back and it intertwines with the crystal operator. So in that sense, yes, there is an RSK flavor of the crystal operators. Does that answer your question?
I didn't, when I asked the question, it was before you got into the RSK stuff. And then when you did,
okay.
I could see, but yeah, great.
Okay, I actually have a question if no one else has one immediately. Have you, so since these are kind of generalizations of Schur functions in some sense, have you thought about de Moivre truncations of them? Like, does that even make sense? And would that be interesting? Like, is there anything there?
Yeah, yes, I think you can yeah, you can, so instead of looking at symmetric Grothendieck, you can sort of look at sort of like the Schubert analog of them. And yeah, you would get some sort of de Mazur truncations. We haven't looked at that because we've mostly focused on the, well, in this paper, we have only focused sort of on the uncrowding. But yes, you
I
can.
mean, you have a crystal, right? So it makes
Yes.
somehow, it's like, obviously you want to cut it up.
Yes, yeah, you can do that.
Do you know, like, what would they correspond to? Because I asked this question and Stephen kind of answered, about whether the Grothendieck polynomials have some sort of representation theoretic meaning in terms of being modules of something, or sorry, characters of some module. If you do a de Mazur truncation, what would happen? What would that mean? Either K theoretically or representation theoretically, I mean.
Yeah, those would be, I guess, K analogs of the Schuberts.
Okay.
Does that make sense? Yeah.
Sort of. I have to think about it, but yeah, sort of. Thank you.
Well, Kari, maybe now's a good time to stop the recording, or I think Anna